I'm going to start off chapter 5, and I'm going to teach all of 5.1 through 5.3 in the same lesson. That's because all three of these are teaching you three different ways to do something, and I'm just going to simplify it down to the best way to do it. That way you don't have to worry about doing three different things in different scenarios. So it has to do with lines. So here we go. So you'll see the name of this chapter is Systems of Equations. And equations are, just ways we write out lines. So y equals 2x plus 4. An equation just means there's two variables. We could also write it something like 3x minus 2y equals 6. Right? So these are equations. So systems of equations are when we group up two different equations together. So instead of just talking about one or the other, we're talking about two groups together. And we've actually worked with these before. Think of our money problems, where we say if he has 10 coins in totals, so if he has some dimes plus some quarters, that equals 10 coins, and then the total of the coins equals $150 equals 0.10d plus 0.25q. Find the number of quarters and dimes, right? So in this type of problem, when we're talking about quarters and dimes, we have two variables and we want to figure out what our variables are. Same thing when we're just working with x and y. We have two math sentences. That's the system of equations. It's when we have a group of math sentences. If we have two variables, we want to solve for our two variables. So that's what it means. Systems of equations are just solving for both our variables. Now the way we want to do this is just thinking of them as lines. So let's so the first thing we want to do is we just want to convert both of our math sentences into y equals something. We want to solve for y. We want to get y by itself. So this first problem, y is already by itself, 2x plus 4. And in our second problem, to get y by itself, I'll go ahead and give it to you. It's y equals 3 over 2x minus 3. Okay, so this is our system of equations still. We got two lines, and then over here, let's think of our dimes and quarters problems. When you don't have a y, just pick one of them. So let's get d by itself in both instances, 10 minus q, and q is acting as our x. And then we'll do the same thing. Oops. Okay, so that's really the gist of it if we wanted to graph it. And let's see what it looks like when we graph. And okay, so we have graphed our two y's, and we'll see we got two different lines, and somewhere along the line they will intersect. All right, so really when we talk about solving for these equations, solving for systems of equations just means find the intercept. So what we want to do is we want to turn them into lines and then graph them, and we can find it that way. Now obviously we're not going to have our graphing calculator all the time, so in the next step I'm going to show you how to solve it on paper, but let's take a look at our dime example first. Alright, so in our dime example we have our two lines graphed. Oop, where are they at? Alright, and the intersection doesn't make sense in this case because I didn't pick good numbers, but it would mean you would need negative 42 quarters and 435 dimes to make our statement true. Obviously, that doesn't make sense. In our case, maybe if I made it 100, no. Anyway, the point is the intersection is the values that makes both statements true. So solve for systems of equations, turn them into lines, graph them, find the intersection. Now, if we didn't want to graph it, this is what we would do. You've actually done problems like these before with substitution. But we don't need to, we'll just go from the problem we already have here. All right, so if we want to solve it on paper, we've done this before with substitution. See how we have y equals this and y equals this. That means these two things are equal because they're both equal to y. So we can actually set these up in a problem equal to each other. 3 over 2x minus 3. And what that does for us is now we're only working with one variable. So we'll just solve it like a normal equation. We have a denominator, so we'll do clearing fractions, multiply everything by 2. Oops. 4x plus 8. Oh my goodness, what is wrong with my pen? 4x plus 8 equals 3x minus 6 minus 3x minus 8 minus 8 minus 3x. X equals negative 14. If x equals negative 14, we can plug it back in up here. X equals, or y equals 2 times negative 14 plus 4. Y equals negative 28 plus 4. Y equals negative 24. So that means our x coordinate is negative 14. Our y coordinate is negative 24. And remember, that means that's the intersection of our two lines that they gave us. And if we go back to our graph, we'll see that our graph is meeting at negative 14, negative 24. So we'll do one more example. On page 159, we have example 5.2a. We have 5x plus y equals 13, and we got 2x minus 3y equals 12. It says solve the system by substitution, but doesn't matter what they say by. I just want you to know how to solve it. And remember, we'll just start by turning both of them into line equations, which means solve for y, which means get y by itself. So getting y by itself over here, we have y equals negative 5x plus 13. That's an equation of a line. Over here, we've got, it's going to take an extra step. This is going to equal negative 3y equals negative 2x plus 12, and then divide by negative 3, divide by negative 3. So that's going to give us y equals 2 over 3x minus 4. And so now we've got two equations of a line. Now we could, like I said, graph it at this point, but let's go ahead and do it on paper by setting both of these values equal to each other. Since we know they're both y, that means they're both equal to each other. So now we're just solving for x. Let's clear our fractions by multiplying everything by 3 times 3 times 3, negative 15x plus 39 equals 2x minus 12. Getting this 15x plus 12 plus 15x plus 12, and we're just combining our terms, so that gives us 51 equals 17x. X is equal to 3, and if x is equal to 3, we can substitute that back into one of our problems. Let's see this one up here. 2 over 3 times 3 minus 4, cancel, 2 minus 4, negative 2. So our x is 3, our y is negative 2, and we can show this by graphing, which I will do in just a second. What are our two lines? Our two lines are y equals negative 5x plus 13, and y equals 2 over 3x minus 4. Okay, and the solution is going to be whatever we said it was right here. 3, negative 2. Oh, did I have that backwards? No, we had that right. 3, negative 2. All right, perfect. All right, there are two special cases, and those two special cases are, one, when we're working with the exact same line, y equals 2x plus 1, and y equals 2x plus 1. They don't have an intersection, just they're the exact same line. So everything is the same between them, and then the other possibility is we got two parallel lines where there's not going to be an intersection because these lines never touch. Like always, write down your questions so we can go over them. I know I threw a lot together in one section here, but it is a little bit of what stuff we've done before. So yeah, we're just turning them into lines. Just think of it as solving